ICNTRT. So it is my pleasure to introduce the next speaker, Professor B. Kumar Murthy from University of Toronto. So I know him for 4 decades now. He gave courses, lectures in so many institutes all over India, including HRI. So today he will be talking on zeta 3, log 2 and pi.
Yeah. Thanks, Adhikari. Thanks to the organizers for the invitation to be here. I was, if you look at the printed program, you'll see that I had a different title on the program. So because I was trying to decide which of several talks that might be appropriate for this place. And initially I thought since Kalyan and Srini are both closer to analytic number theory, I would speak about some work on divisor functions. But then some people here asked to hear this talk again, which I gave recently in other places. And so I agreed to do that, not out of any main reason is that I didn't have to prepare any new slides. So I could use the slides that I already had. So this is a talk about zeta of 3. Can you, there is no adjustment on this. This one? Like that? Is that better? I can't really see it. Is that any better? I can also speak up to maybe that's better. Okay, so the topic is zeta of 3, log 2 and pi, numbers that we all know and kind of love, and about the relationship between these. They are somewhat familiar, but they're also very mysterious in other ways. Okay, let me see if I can do this. Yes. So a subtitle for this talk might be from Euler to Grothendieck, because it's a story. It's a story of ideas that actually started even before Euler, but certainly one to which Euler contributed a lot, and set in motion a certain kind of way of thinking that is still alive and has found new energy and new insight thanks to Grothendieck's perspective, and I'll explain what I mean by that. Okay, so the first thing is sometimes when we think about familiar results, that we've read about or we know about for a long time, we forget there's a history to them, and that history is what brings those results alive. So when Euler was young, age 27, maybe not so young, but somewhat young, there was a famous problem that people were trying to solve. Everybody was trying to solve in Europe, the sum of the reciprocals of the squares. What is it? Try to find a closed form expression for that. The Bernoullis were trying, other famous mathematicians were trying, but Euler solved it, and he solved it in a very spectacular way by giving this really simple formula, pi squared over 6, and people were astonished and happy with that. And Euler became a celebrity. He was a much sought after mathematician after that. So that was a career building event for him. But it naturally raises the question of what about zeta 3? By the way, I'm not defining the zeta function because I'm presumably there's a number theory audience, you all know what it is. Zeta of 2 had been evaluated, now can we evaluate zeta of 3? And that problem has stood the test of time. Even though it was raised a long time ago, it has not been solved. And so much attention has been drawn to this problem that even in the popular literature, such as the book, the cover you see here, In Pursuit of Zeta 3, there is a description of how difficult this problem is, that the very different things people have tried, even from a popular point of view, to explain that this is a hard problem. Now, Euler did try very hard actually to find a simple symbolic formula. Symbolic formula is the words of Nahin, this author of this book, but tried to find a simple formula. As we go through the discussion in the next half hour, 25 minutes, keep in mind this whole question of what does it mean to find a formula? When you ask what is zeta of 3, well, zeta of 2 is pi squared over 6, sort of by implication you want zeta of 3 to be expressed in numbers that you're already familiar with. But the upshot of what we're going to say is that that concept has to be rethought, and I'll say more precisely what I mean by that. So Euler, as I said, tried hard to find out a formula for zeta of 3, and in a paper published after his death, he asks this sort of rather startling question. zeta of 3, is it true that there are rational numbers alpha and beta such that zeta of 3 is log 2 cubed plus a rational multiple of pi squared log 2? And this is documented in a beautiful, easy to read paper in the American Math Monthly by Dunham, Euler and the cubic Basel problem. That's what they call it, the cubic Basel problem, probably because he was in Basel at the time. So it's again this formula that Euler is conjecturing, although it has undetermined rational numbers in it, it's still as startling as zeta of 2 equals pi squared over 6. And so there he stuck his neck out and made a specific guess what might be. So the first question you ask is, where did log 2 come from? You know, pi was already there. Zeta of 2 had pi, so you think, okay, pi will probably be involved in other values. Where did log 2 come from? In his attempts to evaluate zeta of 3, he came up with many expressions, some involving integrals. So there's that first one that zeta of 3 is 2/7 pi squared log 2 plus 16/7 times his integral of x log sine x. He didn't evaluate that integral x log sine x. However, there's a superficially similar integral that he could evaluate, namely log sine x, and that's a rational multiple of pi log 2. So that might have led him to think, well, this might be something similar, maybe more complicated, but somewhat similar. Notice also, by the way, in this version of Euler's conjecture, there is no pi cubed. It's a rational multiple of pi squared and log pi squared log 2 and log 2 cubed. So what is zeta of 3? So I said we were going to think about what do we mean when we ask for a formula. In a nutshell, I want you to think that by the end of this discussion, you will say that zeta of 3 is zeta of 3. So when we ask for, when you first what is pi? Many people tried to find what is pi. Now we understand pi is a universal constant. And you can find various expressions, some infinite series for it, but basically pi is the fundamental number here. Similarly, we have to start thinking of a whole family of numbers that are sort of primitive in a way, not in a formal way, but it seems to be they're the building blocks of the kind of numbers that we are able to understand properties of. Now, amongst when I say these are typical of what do I mean, that family of numbers, the ones I want to draw attention to are periods. Periods are what? Traditionally, periods means you take a differential form and integrate it on a cycle. That's what you get a period. So many of the numbers that we've been successful in studying, either for example proving their transcendence or algebraicity, transcendence especially, are numbers that we can interpret as periods. So maybe we should be thinking of periods as the fundamental building blocks, and then we want expressions for anything in terms of periods. So what is a period? Here's a very explicit formulation by Kontsevich and Zagier, that it's an integral of a rational function on a semi-algebraic set. So you have two polynomials f and g with algebraic coefficients. You take their quotient and integrate it on a subset of the Euclidean space, which is defined by polynomial inequalities. Okay? That's an explicit definition of a period. So anything you can write in that form, they call a period. So that takes there's no explicit algebraic geometry in the definition of that. So here is an example of a period, log 2. It's the integral of dx over x on that semi-algebraic set, namely the interval from 1 to 2. Pi is a period because you can write it as a volume form on the disk. Okay. But here is another period. Suppose I take an iterated integral. Iterated integrals, by the way, are things that you can think of as coming from calculus, but also you could think of in terms of Chen's theory in the context of mixed motives. So if I integrate dx over 1 minus x, dy over y, dz over z over that range, so you undo the iterated integral into three integrals and you write it out in that form. Now what you do is you expand that 1 over 1 minus x. So actually you do the inner two integrals and you'll get log x squared over 1 minus x from 0 to 1. And now you expand 1 over 1 minus x as a power series. So you write this as a power series of 0 to 1 log x squared x to the k dx summed over k. And now that integral of course can be evaluated. You use integration by parts twice. And what do you get? You get summation 1 over k plus 1 cubed. In other words, zeta of 3. So this iterated integral at the top is zeta of 3. So therefore, zeta of 3 is a period in the sense of Kontsevich-Zagier. So Euler knew this already, and he had this expression. So now we have a level playing field. When we ask for these numbers zeta of 3, log 2 and pi, they're not just random numbers drawn from somewhere, they're all periods. And now we're asking not as precise a formulation as Euler is asking. Let's take a step back and ask a more general question. Are these three algebraically dependent? So in particular, is zeta of 3, does zeta 3 satisfy an algebraic relation involving log 2 and pi? So that's the question we're going to try to address. Now, periods they've been defined by Kontsevich-Zagier in this calculus type of way, but they arise naturally also from algebraic geometry. Namely, you have what is an algebraic variety? It's a zero set of some set of polynomial equations. And now you can take a differential form on that set, and you can integrate it on a subset of that set of solution set. That's a cycle, and you get a number, and that number is considered a period. More generally, one has to go beyond algebraic varieties and also learn how to do the same kind of calculation, namely integrating a form over a cycle, when you work with pieces of algebraic varieties, which are called motifs. And then one has to take one step further, go beyond motifs to things called mixed motifs. But the reason this kind of geometric way of thinking about periods is interesting and important beyond the way Kontsevich-Zagier formulated it is there are some geometric principles underlying relations between periods. In general, you should find, if I'm an algebraic variety which has periods and there's algebraic relation between periods, there's got to be a geometric reason for that. If there's no underlying geometric reason, these periods should be independent, algebraically independent. That's kind of the fundamental idea. And again, to add some content to that, it's because of basic conjectures in algebraic geometry, and they are just conjectures, basic conjectures like the Hodge conjecture or Tate conjecture that say when you have certain cohomology classes with certain properties, they've got to correspond to some algebraic geometric phenomena happening in the underlying variety. So all to say, just to summarize that third bullet point, it is to say that in algebraic geometry there's a way of thinking that turns period relations into geometric phenomena. That's not a theorem, it's a way of thinking, it's an expectation. Many basic conjectures are based on that way of thinking. Okay, in particular, there is a conjecture of Grothendieck, which is such an important conjecture, but it's just a footnote in a paper that he published in 1966 on the de Rham cohomology of algebraic varieties. So in that footnote, Grothendieck suggests that the transcendence degree of the field generated by the periods has a meaning. The transcendence degree of the field that is generated by the periods can be interpreted as the dimension of a certain group. That group is the Mumford-Tate group. So let me see if I have a slide on the Mumford-Tate group. No, I don't have. Then let me tell you what Mumford-Tate group is. Mumford-Tate group cannot be defined directly. It has to be defined indirectly. It's not something like the Mordell-Weil group. You could say it's the rational points on a curve. Mumford-Tate group is an algebraic group that you can understand in one of two ways. An algebraic variety, let's say over the complex numbers, the set of solutions, it's not just a set, it has extra structure. In particular, if it's a smooth algebraic variety, it has a structure of a smooth complex manifold, and therefore it has de Rham structure and a Hodge structure. It has additional structures. The Mumford-Tate group is the smallest algebraic group in the Betti cohomology, the singular cohomology of the variety, which over the complex numbers picks up the Hodge structure. Okay, so somehow it's a group a rational algebraic group that characterizes the Hodge structure. Not characterizes, understands whatever the content is of the Hodge structure. Okay, so it's defined in terms of some complex analytic thing, but it's an algebraic group. Another way of defining it is that it's a group which acts on the cohomology of these varieties and it has certain invariants, and those invariants are exactly the algebraic cycles that we were talking about before. Okay, so two ways of defining. No, that's the last thing is only vaguely correct, but it's okay. So I want to dwell a little bit on this whole Grothendieck conjecture and what it means for periods. And as I said, I'm going to interpret the conjecture. Grothendieck's statement was for pure objects, algebraic varieties. I'm going to interpret it more generally in the mixed context, so for mixed motives. So here is a simple example just to focus on your mind. Suppose you take the projective line. Then the Mumford-Tate group is just the multiplicative group. It's GL1. The period for P1, you take d theta and integrate it on the circle, you get pi basically. And so Grothendieck's conjecture in this setting is saying that the transcendence degree of the field generated by pi is one dimensional, which in other words pi is transcendental. So that is the super special case of Grothendieck's conjecture, but of course in that case we know it as a theorem. Okay, so I want to talk about this work that I did with Payman Askandari. He was my student and then a postdoc. We're standing outside the Fields Institute, and he's now a faculty member in Winnipeg. So it's been a year now already that we worked on motivic Galois groups of mixed motives, especially the unipotent radical, and we were surprised to see that it has this implication for Euler's problem. Okay, so let me give you a little bit of motivation about what I've been used this word a couple of times about mixed objects or mixed motives. What do I mean? So consider the Manin-Drinfeld theorem. It's a classical theorem in the theory of modular curves. So you all know this. You take the upper half plane. Many of you work on modular forms. You take the upper half plane. You mod out by a discrete subgroup of SL2Z. You get an open Riemann surface, which you can compactify by adding a finite number of cusps. So that let's denote by S the number of cusps. Then if you add those cusps, you get a compact Riemann surface. And one of the fundamental theorems that actually comes from theory of modular forms is that this curve has a model over Q. It's defined over Q. That comes from the fact that there's a basis of the space of modular forms with rational Fourier coefficients. Now you can ask, here I have a good algebraic curve. I can take its Jacobian. It's a certain abelian variety. If the genus of X is G, you get a G-dimensional abelian variety. These cusps are points like God given to you. You've got explicit points. So you can ask, when I look at these points in the Jacobian, what kind of subgroup do they generate in the Mordell-Weil group, in the group of rational points? And the theorem of Manin-Drinfeld, and actually you can get, at first, if you're seeing this question for the first time, you can get excited that maybe I get some points of infinite order. But the theorem of Manin and Drinfeld is that in fact that subgroup generated by cusps is torsion. When you take a congruent subgroup, it's not true for non-congruent subgroups. If you take a congruent subgroup like gamma naught n and look at the Jacobian of the modular curve, the cusps will generate a torsion subgroup. And the proof actually is not that hard. It's just a couple of pages explicit use of Hecke operators. But now having that Manin-Drinfeld theorem in hand, we can ask a more general question. Suppose I take an algebraic curve, complete curve, and take a finite set of points on that curve. What is the rank of the group generated by those finite set of points in the Jacobian? Now at first you might think that's hopelessly general a question, because you might have taken in S a Heegner point, or you might have taken a cusp. How will you tell, is it finite or infinite, what the rank could be? But nevertheless, we're going to answer this question in terms of the Mumford-Tate group. So here is the way one starts to think about it. There's an easy exact sequence from the cohomology H1 of the punctured curve, relating that to the cohomology of the complete curve, and then some simple copies of Q. So what it is elements of H1, this middle thing can be written by, elements of there can be written as meromorphic one forms, which are holomorphic outside of S. So what you can do, you can integrate them around little loops around S and you get residues. So that's this map. And the elements on the complete curve, in other words, the ones which extend to S are the ones which have zero residues at all the points in S. So you have this sequence always, but Deligne observed that the question is, does that sequence split? In other words, is there a section from here to here? And what Deligne showed is that the sequence splits if and only if S is torsion in the Jacobian. So he gave an interpretation of the torsionness of the sequence in terms of the splitting of this exact sequence. So in this instance, what it is, this is the first real practical example of a mixed object, because it has these two things, H1 and this Q minus 1, and if you think of this not in the complex setting, but say the Hodge structure or the L-adic setting, see this is going to be weight 1, whereas this is going to be weight 2. So you have an object which sort of has in it a weight 1 piece and a weight 2 piece. So weight you can think of in two ways, either in terms of the Hodge structure, because this is a H2 Hodge structure or H1, or in terms of the way Frobenius eigenvalues have a complex absolute value. Okay. So in this case, you can define a Mumford-Tate group for this object in terms of the Mumford-Tate group of this, and what you find is you get a new object which is now no longer reductive. Don't worry about the technical definitions of these words, you get a new kind of object. And this non-reductive group is non-reductive because it has a unipotent component, but that unipotent component is what's controlling the size of the subgroup generated by S. So here's the theorem. If I have a group curve of genus G, for convenience of the way I'm stating it, I'm just saying it has no endomorphisms other than the trivial ones, then the unipotent radical of the Mumford-Tate group of the punctured curve is 2G times the rank of the group generated by S. So in the case that you expect the group generated by S to be torsion, as in the Manin-Drinfeld setting, it means that the unipotent radical is 0. In other words, that the group is semi-simple, in other words, that the sequence splits, which was Deligne's theorem. So this appeared a year ago in the Pacific Journal. So this theorem is, I believe, the first one that gives an arithmetic interpretation to the size of the unipotent radical. Okay. So now our goal is to build on that. So now we realize the unipotent radical carries arithmetic information. So our goal is to build on that and look at it in another context, namely with certain mixed motives or mixed Tate motives even. And what we're going to do is we're going to construct them almost by hand in such a way that they have large unipotent radical and interesting periods. And then we're going to tie it into Grothendieck's conjecture. Okay, so the final example I'll give you will be in the category of mixed Tate motives, but our results are quite general. So I need to say, what do I mean by a large unipotent radical? So I have a mixed motive, I have a unipotent radical. What does it mean to be large? Well, it's easy to show. It's contained in this piece. You see, the mixed object has two kinds of filtrations, an ascending filtration coming from weights and a descending Hodge filtration. So the unipotent radical is contained in the W minus 1 part of the weight filtration. And to say it has a large unipotent radical means that the unipotent the Lie algebra is equal to the full W minus 1 of NDM. Okay. So here's an example. Suppose I have a mixed motive M, which is an extension of Q of the trivial motive Q of 0 by L. So here we assume that L has a weight, a negative weight P. Then the endomorphism of M will have weight 0 plus or minus P, because after all, what is endomorphism of M? Is M tensor M dual. So M has weights 0 and P, so M dual will have weight 0 and minus P, and you tensor those together and you get 0 plus minus P. And therefore W minus 1 is going to be only the last piece, namely L. Therefore, if L is a simple object, for example a Tate motive, then the unipotent radical, which has to be contained in W minus 1, has to be either 0 or the full L. And it's going to be 0 if the extension is split, and L otherwise. Okay, that's a good case to keep in mind. Okay, and Deligne and Goncharov studied the whole business of extension of Tate motives, and they proved that X1, in other words, short exact sequences sort of like this, where you have a mix of, and you have Tate motifs here and there. Notice I have not defined yet Tate motifs, but it's not necessary for you to know what the precise definition. It's the simplest kind of motif you can construct. But already when you try to put Tate motifs together to create new motifs, it becomes a hard problem. And what they proved is the only way of doing this is either you can't do it at all, you can't create a non-trivial extension, or there's a unique one. So in particular, if I take m equals 3, there is a non-trivial extension like this. And by what I said on the previous slide, because this is simple and has negative weight, the Lie algebra, the unipotent radical of the Mumford-Tate group of this is equal to this. Okay. Now Deligne and Goncharov also computed the periods of this motif, this one that I'm saying exists, this m. They computed the periods. The period matrix has a pi in it and a zeta of 3. Okay, that's the period matrix. So in other words, the periods are generated by pi and zeta of 3. On the other hand, the Mumford-Tate group, we already know, okay, because of this extension doesn't split, the Mumford-Tate group is dimension 2. So Grothendieck's conjecture in this case, which Euler was silent on, is that zeta of 3 and pi should be algebraically independent. I mean, nowadays everybody will say yes, we expect that, but that's a consequence of this conjecture. Zeta of 3 and pi are algebraically independent is a consequence of Grothendieck's conjecture. Okay, now we're going to talk about putting motifs together to create other motifs. This is coming from something we learned from SGA 7. It's called extension panachée in French. I think it means blended extensions. So it's a way of piecing together or patching together two different extensions to create a more complicated extension. So the reason now I've lost track of time, so Adhika, you have to tell me if I have 5 minutes? Okay. So we have a theorem with Payman, which is really the main content of our paper, of how to patch together large unipotent radicals. So suppose you have a motif and a point in the filtration, a negative point, where m modulo that pth part of the filtration is trivial, and the pth graded part of of m is non-trivial. And suppose the unipotent radicals are large at the pth level and m mod the p minus first level, then we can put them together and create a large unipotent radical for the m itself. To do that, we need a certain technical condition, weight disjointedness condition. When you read the precise statement in the paper, you'll see that everything is described very explicitly and combinatorially. So if I give you an explicit example, you can check the condition that it holds. So this gives you a recipe for constructing a lot of mixed motifs with large unipotent radicals. Okay. So now here's the motif that we're going to construct. This horizontal one is the one that we got from Deligne and Goncharov, but we twisted it by 1. Okay, so this came from Deligne and Goncharov. This one is a particular kind of one motif that's described in Deligne's Hodge 3, where there's a let me just say like this: the period here corresponds to pi and log 2, log r rather. The r is here, log r. Okay, so now what SGA 7 tells you is, when you have a sequence like this and a sequence like this, two extensions, you can piece them together to create a new extension, which we call m sub r. And there are some conditions that Grothendieck needs to make this exist and unique, namely vanishing of some X groups, all of which can be proved to hold in the category of mixed Tate motifs. Okay, so therefore you construct an m sub r. And what are the weights of m sub r? Well, this one has weight -8. This one has two weights. This has -2 and 0. So this thing has three weights: 0, -2, and -8. Okay. So if you look at now the weight filtrations, I told you the weights. You can see remember, each of these pieces is one dimensional. Each of these pieces that are going, this is one dimensional. This is now two dimensional because they're made of two one-dimensional pieces. And you can compute how big the weight filtration pieces are. W minus 2 is one dimensional. It's actually it's two dimensional. It's this whole m of 1. And the other condition that I needed, what we payment I needed in our theorem is also satisfied because MR mod W minus 3 MR is NR, which also has large unipotent part. Remember, that's what we needed. We needed W minus 2 and MR modulo W minus 2 minus 1 to both have large unipotent radical. The first one is obvious by the Deligne-Goncharov theorem because it has dimension 2, and N sub r is true also because of the example I gave you of from here. This one, from this example, you can see that the vertical one also has the right dimension. Okay, and therefore, by the theorem, the unipotent Lie algebra of the unipotent radical is large, which means that it's equal to W minus 1 NMR, and that has dimension 3. So therefore, now if you compute the full Mumford-Tate group of this motive, there is the part coming from the graded piece, the semi-simple part, and then the part coming from the unipotent part. The semi-simple part, it's a diagonal Tate type of thing, so it's only one dimensional. So the whole thing has dimension 4. The Mumford-Tate group of this new mixed motive has dimension 4. So it has some periods, namely the periods, you see when you do this, the periods come from the periods of the pieces, and we already know here this thing has pi and zeta of 3, and here they have pi and log r. Let's take r equals 2, then I have pi and log 2. So the periods are pi, zeta of 3 and log r. Now there is a fourth period, because this is a 4-dimensional object. There is a fourth period. We don't know what that fourth period is. This construction is not geometric, it's homological, and so we don't know how to get our hands on that fourth period. But because of our calculation that the dimension of the Mumford-Tate group is 4, growth index conjecture predicts that all 4 of those periods should be algebraically independent. And therefore, it means that growth index period conjecture is inconsistent with Euler's conjecture. And in particular, if you accept growth index conjecture, then zeta of 3 log 2 and pi are algebraically independent. Log 2, as we saw in the construction, there's nothing special about log 2. You can replace it with log r. Actually, there's nothing special about zeta of 3 either. You can replace it with any finite, any odd value. And you can prove more theorems of this kind as long as you can control the disjointedness theorem that we had about large unipotent radicals. You can prove many of these periods of mixed motives have to be algebraically independent. Yeah, okay. So I think that's all I want to say. Thank you. Happy birthday.
Okay, any questions, comment, Ram?
Two questions. First question is, does the growth index conjecture imply the 4 exponentials conjecture? Because they are just logs of rational numbers. And so in those mixed motives that you
I
constructed,
don't know how to construct.
but you got log r's from those mixed
Yeah,
motives.
but log r we have.
And then to use another sequence of log s, let's say,
Yes.
in that sequence that you had, is it
Yes.
possible to extract the 4 exponential conjecture from growth index?
I don't know. My first guess is no, but I don't know.
Okay. Second question is, what if the Jacobian variety had Cm, wouldn't the dimensions collapse?
Dimensions of what?
The Mumford-Tate group that you had.
So the whole.
And so the conjecture
whole
would
of
be-
the Jacobian having Cm is rare.
Mhm.
It may have extra endomorphisms, but I stated a special case, so you can do this. Let's see, how can I do this? You're talking about the Monin-Drinfeld thing.
Yeah, yeah.
Yeah, so here
In
I
that theory.
stated the condition end is just Z.
Hmm.
So we can do this for any endomorphism algebra, and then you'll get it's going to be this condition will be let's see now, it'll be 2G. They won't be exactly 2G. It'll involve that field of multiplication. Yeah. So if it had extra multiplications, you still get a theorem. Michelle wanted to ask.
Thank you. So thank you very much. You mentioned the conjecture of Grothendieck. Can you get further result using the conjecture by Yves André, which contains the Chanel's conjecture, for example?
No, I don't know. Actually, this question has come up before too. I don't know.
Okay.
This is you mean on motivated cycles?
On motifs, yes.
Yeah.
Okay, thank you.
Any more question, comments?
Can this mixed variety setup give something about the odd values of zeta? About the odd values of zeta?
What odd values of zeta? Yes, I think so. You could have done this with two different zeta odd values.
Okay,
And-
and you can keep on doing that?
You can keep on doing that, but now Payman has taken this, maybe others have done this too. The extension panache is only for two extensions, but you can build a deeper level and then you can get any finite number.
Ah.
Any more? Okay, if there is no more question, comments, let us thank speaker again. So, at next talk, it will be at 11. Yeah, is it at 11:50? We start. 3-4 minutes. So it is 50, it will be, it is 46 already. Yeah, 11:50.
Stay like that. So is it coming?
Yes.
And how do I show the pages? Yeah,
Pages are already there. You can scroll from here.
just push it like that. Okay, okay. Thank you. Thank you very much.
And if you want to show something to the audience, you can just use this as a point at this point, and you can point it over.
Okay, okay. Thank you. Yeah. So for this is the on.
Yeah.
Okay. Thank you. Yeah, this is absolutely fine, yeah. So I spoke about this already. Time is up, right?
Yes, sir, we'll announce, sir.
Okay.
So our next speaker is Professor Jyotirmoy Sengupta. So after retiring from Tata Institute in Bombay, TIFR Bombay, he was for a short time in our Vivekananda University, and now he is in IACS Kolkata. So he will be speaking on Benford's law for symmetric powers of holomorphic new forms.
Okay. So I'd like to begin by saying a thank you to the organizers for inviting me here. So of course I know, already said about Kalyan and Srini, so I don't want to repeat that. So I'll begin the thing. So this is about Benford's law. So as I've written, so Simon Newcomb was an American astronomer and he was looking at, what happened?
It's actually, it's locked. Can you swipe it? You can.
What is the key? Passcode? Ah, okay. So he was observing log tables and he found that the pages which had leading digit 1 were more worn out. That means they were more referenced. But this is a bias, why it couldn't be other 2, 3, 9. He was working with base 10, log to base 10. But then later on, much later, in 1938, Benford made the same observation for a variety of sequences. So this bias, now known as Benford's law, so I have given the definition. They are all very natural. So I is an infinite subset, G is some real valued sequence. So those elements of I, such that the first digit of GI is 1. So you define the arithmetic density in the usual way as limit x tending to infinity, the number of x which is in this set, I intersection divided by the total number. And we say that the sequence, this is the definition I have given, but the fact is later on I am going to introduce something called log density, which will show that if this density exists, it must equal this automatically. Okay, so I'll come to that, and why I have written S in 1 inverse, let me see, where's the chalk? Ah, okay, good. So I was considering leading digit 1, etc. So instead of that, if I take a leading digits S, digits S, a given sequence, then the general result is that this density, if it exists, will be log B 1 plus S inverse. So I am taking S only 1, S equal to 1. So I am getting this. So then the set is said to be Benford. So of course, a criterion for the sequence GI to be Benford is that if you take the log of GI to the base B, that should be equidistributed modulo 1. Of course, here if GI is non-positive, I define the log as 0. So examples of Benford sequences, okay. One which follows the law is Gn equal to n factorial, that one. And but the most natural sequence, the identity map Gn equal to n does not follow, have a density. So it's not Benford. So okay, so suppose a set fails to be Benford in the sense it doesn't have the first density, which is called arithmetic. Then we move to another definition, a new density. This is very familiar to more or less called log density. So what is that? That same thing. I am starting with the same function, leading digit 1. So instead of counting the number of i's, I take the sum of I inverse, I belonging to I intersection, and divide by the total. Less than or equal to x, I inverse. Of course, so you can see from this that if I take my set I to be n, all positive integers, natural numbers, then this delta tilde n does exist and is equal to this. But this thing did, so this is an example where the arithmetic density does not exist, but the log density exists. And if we say naturally that the sequence is log Benford, if the logarithm density exists. Now, as I said, the remark, if a set, this is easy to check, arithmetic density, then it also has, and the two are equal. So if I define a Benford sequence to be one which has a density, then automatically has a log density and the value is forced to be this. Okay. Now I come to my interest. I am not really a number theorist, I work in automorphic forms. So and my thesis was on symplectic geometry and representation theory. So from there I moved a long way out. Okay, so the setting is the theorem of basic theorem due to Jesse Thorner and his collaborators. So as I said, so there the basic setup is, so now my I is P, the set of all primes, all primes, and the function g from P to R is Gp equal to AFP, where Fz is equal to sigma n equal to 1 to infinity AFN E of nz. Z belonging to the upper half plane is an element of Sk gamma naught n. It's a primitive form, i.e. a normalized new form. New form of weight k, even of course, k to even on gamma naught n, trivial character. Yeah, so everybody in automorphic forms writes this in this way. Yeah, so I omitted this thing, non-CN. This is important. Okay, this way, why? Because by Deligne, the Ramanujan conjecture, which is a theorem, RC, a theorem says that mod lambda Fn is less than or equal to Dn, where D is the usual divisor function. Is the usual divisor function. Okay, so let me now, I've given Thorner's theorem, let me show it. So as f is as I said, then this density does not have any integer base b greater than 3, those which AFPs have leading digit 1, the density does not exist. So it's not Benford. So naturally, if it is not Benford, the other thing to try is the other density, namely the log density, and they show that the log density does exist, and of course exists means its value has to be this. So it is this one. So it is logarithmically Benford. So let me deal with my result that says theorem 1 holds for sim squared and sim cube. Okay, so a couple of remarks. Expectation should hold for higher symmetric powers of f. And the second, this is a very difficult question. If I assume Ramanujan-Peterson, does theorem 1, just the theorem 1, that is not Benford, hold for mass cusp forms for SL to Z? But here there is a big problem, because the theorem of Thorner crucially uses the Sato-Tate law. The entire proof is based on that. And Ramanujan would get it, you can write lambda fp as 2 cos theta, theta p, where theta p is in 0 pi. But how the cos theta p, whether they actually distributed according to that law or any measure absolutely continuous with respect to Lebesgue, that's we don't know for mass forms. So let me give a sketch of the proof of theorem 1 for sim cube. This in some sense is easier, I mean intuitively it's easier. So let me explain why. Okay. Okay. Okay, so what is sim cube f? So by definition, more or less, and lambda, this is important, the normalized coefficient which is less than or equal to dn. Sim cube f at a prime p, this is the sequence I am studying now. As p varies over primes, this is nothing but lambda f of p cube. Okay? And this is generally true, lambda sim mf of p is lambda f of p m. And we also have the Hecke relations, lambda f m times lambda f n is sigma d dividing the GCD of m comma n lambda f of mn by d squared. So using this you will get lambda sim cube f of p is lambda f p cubed minus 2 lambda f. Okay? So if I think in terms of the continuous variable lambda fp belonging to minus 2, 2, this is nothing but the polynomial x cube minus 2x. Okay? So let's draw the graph, high school. So at 0 this is 0, at 1 it is minus 1, and its maximum is at 2, that is 4. So put it here, somewhere here, 4. So the graph is something like this. Okay. and it's an odd polynomial, this is this side. So why is this easy? Because you see, it will be just the mirror image. This is an odd polynomial, so this variable one, if it's a random, as you can see from here, the area under it basically cancels out. So it has mean 0, it is random that way, intuitively. Or in other words, what I am trying to say is, if you look at sigma p less than or equal to x lambda sim q f at p, this is small o of pi x, which in terms Sartor-Tate is an asymptotic measure. So in terms of pi x, so the leading term is 0. That is what this says. And then you have to compute the values. Okay, let me just continue. So in his proof, Thorna et al. Constructs some intervals where the primes won't satisfy some specific intervals. Okay. So let me just see if I have written that. No, anyway, basically to get the leading digit 1, so something like b power minus j and something by b power minus j plus 1 something, and so he wants to know he computes the Sartor-Tate measure, and there is some, okay, so there is a lemma, but that gets more technical. So I am saying ultimately you choose something where you want to show that this measure is has a lower bound. So here what you have to do is, you have to take the inverse image of this, because this is lambda f. Now you want lambda, so let me write, say, some suitable interval, say alpha beta. Belonging to, so this is odd, so let us put 0, 4. Note that mod lambda sim cube f p is less than or equal to number of divisors of p cube, that is equal to 4. So you can write lambda sim cube f p as 4 cos phi p with just like the sim 1 f, that is f phi p belonging to 0 pi. And now this you put, and you have to take the inverse image of this and compute the integral. So that is not difficult to do, one has to be a bit careful, and it works. As I said, here it is intuitively clear, because on the nose it is random, its mean is small o of pi of x. So the right amount of cancellation is taking place, and this measure becomes absolutely continuous. So you have to basically compute take the roots of this and find this thing. So that will again be some interval, and you compute the Sartor-Tate measure of that interval, and that is positive. So that is how the proof goes for the first part. The second part requires a little more some more calculation. But I think it should be possible to do it by induction. Although I am not clear even to move from Yeah, so I should also give the square there here. That's interesting for the proof. Lambda sim squared f p, this is now lambda f of p squared. So this is nothing but by the Hecke relations, it is lambda f p the whole squared minus 1. So let's compute the mean of this. So I'm looking at sigma p less than or equal to x lambda f squared p minus, that is basically pi x, is just pi x, the second sigma 1. So if I want this to be random, I should have better have this as 0, but this works out because if you compute this limit, then you will get that this, the leading term there is that you can put 2 cos theta p and compute. Actually, Ram has long ago he computed this for mass forms in some paper, I think in Rocky Mountain Journal or something. So the proof is the same once you write it in the same notation there. So he had assumed Ramanujan, otherwise you can't proceed. So this is again random, so it apparently looks like this might be larger, but it's not. So the difference is small o of pi x, and that's the crucial fact basically. And here is, as you see, it's easy to compute the measure. So if I want lambda f squared p, so where does this lie? Minus 1, that is this. What's the difference here? This belongs to minus 1, 3, because this is non-negative, minimum value is 0 and at a maximum 2 by 2 square is 4, 3. So this is asymmetric. So one might say that the average might become large, but then this shows that it is small o of pi x. Maybe one can compute this breaking up. So if I write this as now 3 cos, let's write theta sim squared f of p, then cos theta sim squared f p belongs to minus 1, means it will give minus 1/3, this is the value of the thing, and 1. So you take the inverse cos, this gives you 0, this gives you some pi by 2 from just maybe 20 degree or something, and then you compute the measure. So if I have to compute this, say in a given interval, lambda, yeah, this is easier that way, f square minus p belongs to, say, an interval alpha beta belonging to my minus 1, 3. So what do I get then? Then I get mod lambda f p squared is 1 plus alpha comma beta, I mean this. But the minimum value of alpha is minus 1, so even if I put minus 1, 1 plus minus 1 is 0. So because the square has to be non-negative, because lambda f p is all real, and at the maximum 3 it is 4, so it's root. So it's just the Sato-Tate measure twice, because mod lambda f p squared, so implies mod lambda f p is the Sato-Tate measure of the interval square root 1 plus alpha, square root 1 plus beta. Note that these are all positive. This is at least 0, so this is larger than 0, and because I mod lambda f p has to be this, so the total measure will be 2 times the Sato-Tate of this, and you can compute this. So that would be 4 by pi. I think you write it in terms of cos inverse. So, cos is a decreasing function, so the larger value will come here, yeah. Beta, and there is a sign change when you take that measure, so if I change it, then it will, I also get this actually, 1 plus alpha to, I have to check the sign, cos inverse square plus beta, then sine squared theta d theta. So, you have to compute an integral like this. Let me see if I put the limits correctly. No, this should be below, this is smaller, okay. So, you can explicitly compute this and show it's positive, and you need it for certain intervals of the, say of the form like I have my fixed base b. So, something like this intervals, and this you can prove. Yeah, so this is how the calculation proceeds for the square and the cube. Basically, once you handle these two, the higher powers are, if m is odd, then it's an odd polynomial. There are only odd powers there, and it's even, it's only even. So that way it should be possible to compute all higher powers, but I haven't checked everything, I checked only these two. Okay. So do I have, how much time I have? 5 more minutes? 4 minutes, okay. So as I said, I don't know, this I posing a question because I think in one case this should be obvious, namely there is an example for mass forms, old example of Sarnak, Peter. So, Sarnak constructed some mass cast forms on gamma naught d, where d greater than 0 is a fundamental discriminant. Having integer Fourier coefficients. Integer Fourier coefficients. I mean, this is normalized. Mass, it is always with lambda fn, Fourier coefficients. And he showed that they are attached to Galois, to two-dimensional even Galois representations with projective image PGL2C image, either the dihedral group or the tetrahedral group. And by very construction, this mass form obeys the Ramanujan conjecture and Selberg at all places. This form obeys the Ramanujan conjecture at all places. All places, in particular, it has Laplacian eigenvalue for minus Laplacian, otherwise it will become a negative operator, is 1/4, that the bottom of the spectrum, and mod lambda fp is less than or equal to 2. So here I think the Sato-Tet is nothing but Chebotarev density, right? So maybe one should be able to compute it for the symmetric path of this on the nose. Because symmetric square lift always exists. Gelbart-Jacquet proved it for anything. So, and cube also by Shahidi. So one would this maybe as a toy case one can try the Sarnak thing. It should work, and things should be very easy here. Okay, so that's what I wanted to say.
Okay, any question, comment? Okay, if not, let us thank the speaker again.
Okay, thank you. Oh, this is there. Okay, great. Yeah. Oh, I have to stand here. Oh God. This will go away.